This slide serves as a review of what we talked about in previous session, which was case number 1 of problems. Case number 1 is whenever you are looking for calculating head loss, given pipe length, pipe diameter, and flow rate. As I told you before, case number 1 types of problems, they are straightforward because they can be used using algebra. Now, in today's session, I'm going to talk about case number 2, and then after that, case number 3. Case number 2 is the case that you are going to find flow rate or velocity given head loss or pressure drop, pipe length, and also pipe diameter. These types of problems are a little bit more complicated than case number 1 because it requires an iterative approach, and you will see how. And finally, case number 3, which is very common among civil engineers and is also called design case, is when you are designing pipe diameter given flow rate, length of the pipe, and head loss. This problem also requires an iterative approach, so it's a little bit more complicated than case number 1. Both case number 2 and case number 3 can be solved using Excel. In this class, I'm going to show you how to solve them manually, and then in the next class, I'll show you how to use Excel to solve these kind of problems. To give you a framework how to solve problems in case 2 when flow rate or velocity are unknown and D, L, and HL are known, I have provided a procedure for you, some steps to take. So number 1, and let's go through this process. It might be a little bit difficult to imagine right now, but in next slide, I'm going to go through an example so everything will be crystal clear. Right now, bear with me and let's go through this procedure from number 1 to number 7. It's going to be very useful for you when you are solving problems. So step number 1, you need to apply the energy equation. Remember, we don't have the values for velocity or flow rate. So when we are writing energy equation, we will have two unknowns. One would be velocity because we don't have the value of it, and the other one would be HL. Why? Because we don't have the value of F, or resistance factor, or friction factor, right? So next, because we have the value of D, and we know the information about our pipe, we can find the relative roughness, K sub S over D. Now, we need to guess a value of F based on K sub S over D. Why do we guess that? I'm going to sketch schematic Moody diagram. This is Reynolds, and this would be F. And then on this axis, I have K sub S over D, right? And these are, let's say I'm just going to have 3 of these. Perfect. Okay. So in order to find a value of F, we need to have K sub S over D and Reynolds. However, Reynolds is equal to what? Is equal to velocity times diameter divided by kinematic viscosity. We do not have velocity, so we cannot have Reynolds value to find F. As a result of that, we need to find K sub S over D. Let's say it is this one. And then based on this, guess a value of F. What would be a good guess? If we imagine, remember the fully developed turbulent flow was on the right-hand side of this dashed blue line. If your guess is somewhere over here, because this is almost a straight line, so your guess is going to be pretty accurate. Okay, so you're going to guess a value of F, and then based on your guessed F value, you will be able to solve energy equation for V, velocity. Once you found velocity, then you get Reynolds number, and now that you have both Reynolds number and K sub S over D, you can find another F value. If this F value is equal to the F value that you guessed before, then the problem is solved. Everything is done. If it's not, then you need to do some iteration. You need to repeat this process until these two F values are exactly the same. And once the two F values are exactly the same, then you will be able to calculate flow rate based on the flow rate equation, which is Q is equal to A times velocity. Okay, so this is the procedure. We're going to do an example, and you will see that this procedure is very useful when it comes to the practical examples. In this example, we are going to find flow rate, and as soon as you see flow rate, you should conclude that this is a case number 2 problem. So it needs iteration. We have the type of the pipe. It is a smooth concrete pipe, so this will help us to find K sub S. And then we know how long the pipe is. This is our L. We know the diameter of the pipe. This is D. And kinematic viscosity is given to us over here. This is nu. And the elevation difference between the center of the pipe and the surface of water in the reservoir is 15 feet. So this elevation difference that I am showing to you, this is 15 feet. All right, so I'm going to use the procedure that I showed you in previous slide and go step by step. Step 1 was to write energy equation. And energy equation should be familiar for you, and I'm going to rewrite it again starting from pressure. But before that, I'm going to select my two sections. I'm going to select this as section 1 and over here section 2. Why? Because these are the surfaces that I have most information. Velocity in the pipe is going to be V sub P, and velocity of jet of water that going out of here is going to be velocity 2. Because the diameter of the pipe is constant along the pipe, then velocity at section 2 is equal to velocity inside the pipe. All right, so knowing that, I'm going to write down the energy equation between sections 1 and 2. And here is the energy equation. Note that alpha, or velocity correction factor, we are going to assume alpha is equal to 1 because the flow will most probably be turbulent. We can check this. We can check if the flow is turbulent when we have a Reynolds number calculated. All right, so let's see what we know so far. We know that pressure at section 1 is equal to 0 atmosphere. Pressure at section 2 is 0. Velocity at section 1 is 0. There's no pump, so HP is 0. There are no turbines, so this should be HT. Let me correct it. HT, head of turbine. There's no turbine in the system, so this is 0. And what else? We know that there is going to be head loss, HL, and there is delta Z. So that's it. I can write down HL over here. HL would be equal to F L over D, velocity to the power 2 divided by 2G. All right, so in this, I'm going to call it velocity P, and also this is velocity sub P as well. All right, so let's reorganize this equation and rewrite it again. Z1 minus Z2 would be equal to, alpha is equal to 1, so I will write velocity sub P to the power 2 divided by 2G plus F L D velocity P to the power 2 divided by 2G. All right, here we have delta Z. Delta Z is known, so we have this value. We do not have the value for velocity sub p. We do not have the value for f because, so this is unknown, and also this is unknown because we don't have the Reynolds number. We need velocity to calculate Reynolds number and to get f. We do have the value for the length of the pipe. We do have the value for diameter. So the unknowns are velocity in the pipe and f. So we cannot solve this equation by its own. We need to come up with another way, an iterative way to solve this equation. And that takes me to step number 2. Step number 2 is to calculate k sub s over d, right? And I know that k sub s, based on table 10.4 of your textbook, for concrete, if I'm not mistaken, is 0.012 inches. That's for smooth concrete. And what's the diameter of the pipe in inches? So the diameter is 2 feet. 2 times 12 would be 24 inches, right? So as a result, if you calculate this, your relative roughness would be 0.0005. So now you have relative roughness. The third step is to guess F. Okay, how do we guess F based on the relative roughness would be the topic of next slide, in which I have Moody diagram. Now, your question is, how do we know that we have a good guess? And the answer to that is pretty easy. So first of all, you need to find k sub s over d for your problem. I calculated in previous slide, it is 0.0005. Find this number on the right hand side y-axis. So just to show you where it is, this is 0.0004 and this is 0.006. So the line that we are looking for is in between these two lines. I am going to go over it and show it to you. So this is going to be the line that we are looking for. It is exactly in between the two other lines. Now, what would be a good guess for friction factor for F over here, based on the green line that you can see on the Moody diagram? So take a look at the fully rough turbulent flow area for the green line. It is from here all the way to here, right? And it is a straight line. So no matter what you pick on that line, your F is going to converge pretty fast. Why? Because the straight line, because it's a very similar to a straight line, the value for F is not going to change a lot. So what I'm going to do is simply consider this as a straight line and continue on this straight line until I have an F value. So this is the point. So I'm going to consider my first guess, my first friction factor, to be 0.017. Okay, remember that this is our first guess. Okay, so this is the F value that we are going to use in the energy equation to find velocity, and then use that velocity to calculate Reynolds number. And then based on that Reynolds number, we come back over here and calculate F again. If the two F values that we calculated are equal, it means that our guess was correct. Done. If they're not equal, then we need to continue this iteration until F values converge. Now, let's go to the next slide. I will explain how it works. I have summarized what we have done so far. We wrote energy equation, we had two unknown variables, and then based on K sub S over D, we guessed an F value. So this is our guessed F value. We're going to take this and put it in the energy equation, and in step 4, solve energy equation for V sub P, velocity in the pipe, right? Because that would be the only unknown variable in the energy equation. If you do that, the velocity would be almost 10 feet per second. All right, now that you have velocity, you can calculate Reynolds number. And Reynolds number would be equal to velocity times diameter divided by nu. So I am going to write it over here. It would be 10 feet per second times 2 feet divided by 1.22 times 10 to the power negative 5 squared feet per second. And Reynolds number, if you calculate this, is 1.6 times 10 to the power 6. So first of all, this is way larger than 3000. So our flow is turbulent. And our assumption that alpha was almost equal to 1 is correct. Now, second of all, now that you have Reynolds number, so you have calculated Reynolds, and also you have K sub S over D. You can go to Moody and calculate a new F. And then we will compare this new F to our initial guess and see how they compare. And that's what I'm going to do in next slide. Again, I have summarized what we know. Reynolds number, K sub S over D. I'm going to start with Reynolds number. It's 10 to the power 6, which is over here. And then the number behind it is 1.6, which is like over here, approximately, right? Now let's find K sub S over D. I've done that before, so it was in between these two lines, right? So if I want to show it using the green again, it would be something like this, right? Okay, now I am going to continue this 1.6 times 10 to the power 6 until it crosses the green line. So it would be something like this. So this is the cross section. Now continue this line to find F. And as you can see, it is very, very close to our guessed value. So this reads 0.017, which is equal to our initial guess. Initial guess was 0.017 as well. So we can tolerate an error percentage of like 2-3%. This is basically very close to it. So we are going to accept this number. So we will accept F to be 0.017. Now, because we accept this number, we are going to accept our velocity, which was 10 feet per second, right? Now we can calculate, with this information, we can calculate flow rate that we were asked to. So flow rate in the pipe is going to be velocity sub P times area. And then let me change the color so you can see better. Flow rate would be equal to velocity is 10 feet per second times area would be pi over 4, diameter to the power 2, and the diameter was 2 feet to the power 2. If you calculate this, flow rate would be 31.4 cubic feet per second. And this is the flow rate in the pipe. So in this example, we didn't need to iterate because our initial guess was pretty accurate actually. So based on that initial guess, we calculated F and compared that to the initial guess. Because it was equal, Then we accepted F, we accepted velocity in the pipe, and calculated flow rate. This is the process. Now, what if the calculated F is not equal to initial guess? Then you need to use the calculated F and go through the process again and compare calculated F to the second step. Now, we're going to solve another problem that requires you to do more trial and error, but have this for now. This was just to familiarize yourself with these types of problems. So the third case is the design case, where you are going to find the diameter of the pipe, having the value for flow rate, length, and head loss. Okay? Now, again, this procedure is going to be helpful to you. Since you are going to find D, or diameter of the pipe, you will write all the equations in terms of D, and then you will guess an F, right? And then once you guessed an F, you will solve the equations to find D, then use the D that you found to get velocity, Reynolds number, and K sub S over D, and then find F based on K sub S over D and Reynolds. If this F is very close to or equal to what you guessed, then the problem is solved, and then you can go ahead and calculate your diameter. If not, you need to do some iteration until these two values converge. Okay? And so how to accept the value of D, or diameter? You need to use the larger standard pipe size. And this leads me to the topic of standard pipe sizes that I'm going to talk about. In this example, which is a design example, you are asked to find pipe diameter. So whenever you're asked to find pipe diameter, your mind goes to case 3. So we know that Q is 0.002 cubic meters per second. We have we have temperature of the water. So you can use this temperature, go to the appendix table of your book to find kinematic viscosity. We know that the length of the pipe L is 400 meters, and the head loss should not exceed 30 meters, meaning that the maximum head loss, or HF, pipe head loss, is 30 meters. We're going to use Moody diagram, and K sub S, or sand roughness, is 0.0015 meters. All right, so this is a case number 3. What I'm going to do is first write Darcy-Weisbach equation. You might still remember that Darcy-Weisbach equation was like this. All right, so in this equation, we do not have the value of friction factor, and we do not have the value for velocity. Why? Because velocity can be calculated as Q divided by area, right? Now, we have the value for Q, which is 0.002 cubic meters per second, but the value for area, which is pi over 4 d to the power 2 squared meters. We do not have d, right? We do not have diameter. So if I reorganize this equation and write it in terms of d, velocity would be 0.00254 divided by diameter to the power 2, and this is meters per second. Okay, now I have velocity in terms of d. I can put it inside my Darcy-Weisbach equation and rewrite Darcy-Weisbach equation like this. So I'm going to insert the numbers. I know HF is 30 meters. Let me change the color. So HF is 30 meters. F, I do not have the value for. Length of the pipe is 400 meters. Diameter, I do not have the value for. Times velocity, I just calculated. Velocity in terms of diameter can be written as 0.00254 divided by diameter to the power 2, and the entire fraction to the power 2 divided by 2 times g, and g is 9.81 meters divided by seconds squared. Perfect. So now, again, I have two unknown variables over here. One is f, the other one is d, diameter. So I'm going to write this equation in terms of diameter like this. It would be diameter to the power 5 is equal to f 400 in the numerator, 30 is my HF, head loss, times 0.00254 to the power 2 divided by 2 times 9.81. All right, so I'm going to call this equation equation 1. So now I need to guess a value for f, but this guess is a true wild guess. Why? Because I do not have the value of Reynolds number. How come? Reynolds number can be written as Reynolds number is velocity times diameter divided by kinematic viscosity, right? And I do not have diameter, and I do not have velocity because velocity is a function of diameter as well. So if I simplify this equation and write it in terms of diameter, and if you find new from the tables in the appendix of your book and insert it in this equation, eventually your Reynolds number would be 2,550 divided by d, which is the diameter. I'm going to call this equation equation 2. Now, another thing that you need to find friction factor F is K sub S over D, or relative roughness. So K sub S over D, obviously we do not have the diameter, but we do have the value of K sub S, so I'm going to write it over here. And K sub S is 0.0015 times 10 to the power negative 3 because I want it with the units of meters, and D is D. Now I'm going to call this equation 3. All right, so next step is guess a value for friction factor, or F. And again, as I said, this is going to be a very wild guess. Why? Because I do not have the value for Reynolds number, and I do not have the value for K sub S over D. So I'm going to just go ahead and pick a number that I think is reasonable. I'm going to say that F for my initial guess is 0.01. Just an initial guess, and don't worry about it. It's going to converge. As long as your number is too big, like 100, 1000, or too small, like 10 to the power negative 12, it's going to converge. So don't be worried about choosing this initial F number because it's going to converge pretty easy. So I'm going to take this F, and then what I'm going to do is to put this F in equation 1 to calculate what? To calculate diameter, right? And if I do that, then diameter would be 0.034 meters. Okay, so equation 1 had only two unknowns, F and D. Because we already guessed F, we're going to put F into equation 1 to get diameter. Now, when you have diameter, then you can put it in equation 2 to get Reynolds number, right? So, and when you do that, the Reynolds number that you get would be equal to 7.5 times 10 to the power 4, which is larger than 3,000, and our flow is turbulent. Okay. Now, I can also calculate relative roughness by putting D into equation 3. If I do that, relative roughness, or K sub S over D, would be equal to, let me take a look at my notes to remember that, it would be 0.4044. All right, so now that I have Reynolds number and relative roughness based on my guessed F value, friction factor, I need to use the calculated RE and K sub S over D, or it should be a capital D, to find new F from Moody diagram. If the calculated new F from Moody diagram is equal to my guessed F, perfect. My guess was perfect. If it's not equal, or if it's not close to my guess, then I need to do some iteration. Repeat this process until the two numbers are equal. So because this is a wild guess, it's not like case number 2, there are chances that your F is not going to be equal to your guessed F. And then I will show you what to do. So next I'm going to go to Moody diagram and find a new F based on Reynolds and relative roughness. I have summarized what we found in previous slide and this slide. Reynolds number is 7.5 times 10 to the power 4. So 10 to the power 4 is over here, and 7.5 would be somewhere almost over here. And then K sub S over D is 0.4044. Okay, so it would be very close to the line related to 0.405. I'm going to say that it's going to be very close like this, going up, something like this. All right, and then I'm going to continue this line until the intersection with the green line that represents my relative roughness. So it will be over here, and if I continue this line to find F, it would be somewhere over here and this point. So this point represents friction factor of 0.019. And my initial friction factor was 0.01. You can see that they are different. So I am going to right now say that my initial guess is not valid. So what I'm going to do, I'm going to define a second guess. So second F would be equal to 0.019 that we just found over here, right? Okay, so this is going to be my second F. I'm going to go back to the Darcy-Weisbach equation and find diameter based on this second guess. So I'm going to find diameter based on this second guess. Then I'm going to find a Reynolds number based on this second guess. Then I'm going to find K sub S over D based on the second guess, and find another F, new F. If this F is equal to 0.019 or close to it, I'm going to accept it. If it's not equal or close to it, then I'm going to use it as my third guess and move forward. So I'm going to go to the next slide and show you how it works. All right, now, so if you put this second guess of resistance factor into equation number 1, then you get a D, or diameters, equal to 0.038. And if you put it into equation 2, the Reynolds number that you get would be equal to 6.6 times 10 to the power 4. Okay, now you need one more thing to go to Moody diagram, and that's K sub S over D. And if you calculate this using the new D, it would be 0.000039. Use these two numbers, go to Moody diagram, and you will find that the F is equal to 0.019. Look at that. Right now, this F is equal to our guess F. So now we can accept this and select our pipe size or pipe diameter. Now, this D, remember that this is in meters, right? This D in meters. if you convert it to centimeters, it would be basically times 100, so it would be 3.8 centimeters. There is no pipe size 3.8 centimeters, so you need to round it up, and the next larger available pipe size would be 4 centimeters. So the pipe size that you will select and you will recommend would be a 4 centimeter pipe, and this would be your designed pipe size. So this example also showed you how to solve a design problem, or how to solve a case number 3 problem.